Yesterday, I swallowed some food colouring. The doctor says I'm fine, but I feel I've died a little bit inside. Okay, then question 5, the first of the 6 markers. I've made this question particularly difficult because I haven't given you a figure. The most tricky of the 6 markers won't give you anything to help you out. The far easier ones will give you a figure, sometimes even 2 figures to help build your answer. Now, in terms of this one, you've got to know what you need to do on a 6 marker to be able to access your grade or marks 5 or 6 here. You've got to be able to apply a case study. So let's break this question down. What are we being asked today? We are being asked to explain. Hopefully by now you know that means use the so what rule, give reasons why. Just like the Sandspit question, it's a formation question. That means you need to start at the beginning, end at the end, tell the full story, pot noodle this answer. Start at the beginning, end at the end. Remember the pot noodle, it literally starts with open it, just in case anyone was that stupid. Your answer here for your C stack needs to do the same. We've jumped ahead, the C stack, isolated pillar detached from the headland. So you have got to start from the actual beginning of that formation. And you can see I've left a sentence on there actually by mistake. Rocks that make up a headland can support their own weight. That is absolutely crucial. That is actually your starting point here, because you actually start from a cliff or a headland that over time and all those processes that this PowerPoint will go through are broken down to a point until you leave an isolated pillar detached from the headland. It's a 6 mark question, which means you need 2 arguments, unless it's a formation question. This is a formation question, so you don't need 2 arguments. You need an example / a case study. This video will use Langstone Rock as its example on the South Devon coastline. However, if you were to have used Blackhead in St Austell, Blackhead, the headland of St Austell Bay, or actually Gribben Head as well, those would have been accepted as well. So we'll start with the example here. Your example for Cave Arch Stack Stump will need to be Langstone Rock, simply because it has each of those features found on the South Devon coastline. Absolutely crucial, just like the other erosion landforms you've seen. The rock can support its own weight. Therefore, you can have an arch being built within it, because if you can see the arch there to the left-hand side to the image, hopefully you can see that the bottom has been completely eroded out. You can see right through it. The rock above must be able to support its own weight, otherwise it wouldn't be there. Langstone Rock made of breccia sandstone, that jagged mixture of sandstone mudstone. In addition, things to know about this headland: it's a European shag nesting site. That will be important in a moment. And also, you can see trees and grass growing there. Both of those most recent points will be related to weathering in the not too distant future. So, where we start from with this, that diagram on the top left hand side will be on all of the slides, just so we can go through with that one always staying put. All rocks, you have to start from this point that all rocks have natural weaknesses. For example, sedimentary rocks have bedding planes, and if you look across to Langstone Rock, the photo below, hopefully you can see those horizontal lines running through the rock face there. That's an example of a weakness, and the reason for that is, if you imagine a brick wall, and if you were running your finger down a brick wall, you go brick, 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 and then your finger would go into that cement gap, and then brick, 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 cement gap, brick, 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 cement gap. The cement gap here is very similar to these bedding planes, on the grounds that it's just an area where the rock face is ever so slightly indented, or ever so slightly further back. And what that means is the sea can compress air into those weaknesses, therefore hydraulic action occurs, and that will lead to the formation of faults. Faults are vertical cracks within the rock face. Within breccia sandstone, when they match up, or where they meet the bedding planes, you have essentially a vertical line running between the 2 horizontal lines, and that's where your fault begins to form. As one of those build up, you get a line of weakness like that on the diagram over there, but for us at GCSE we can simply call that a fault. So part 2 of your explanation, as a result of some of the breccia sandstone falling into the sea, because the fault's been widened. Obviously some rocks have become loose and fall into the sea. That is now going to be used by the sea in the process of abrasion, where they're going to throw those rocks back, going to scour those rocks on the cliff face. This, coupled with continuing hydraulic action, means that the fault will widen and deepen, eventually forming a cave. Now the cave here, remember, you can't walk all the way through the cave to the other side. The cave will only be an indent into the cliff, it's not all the way through. So a cave, an indent into the cliff formed by erosion. An arch, which we haven't got to yet, is where you can go all the way through to the other side. Okay, at this point, where we move between caves and arches, the next slide is a most able slide. Quite a complicated concept. It's for those students really chasing after the grade 7s, 8s and 9s, but I will go through it anyway. If you want to skip this one, then you're absolutely fine to do so. At your Mabel end, one of the concepts between a cave and an arch is the process of wave refraction that you can see in the diagram there. Waves wrap around the headland because the seabed becomes shallower there, so the waves become slower there, and then wrap the rest of the wave that isn't slowed down around the headland. As a result, the sea's energy is focused on both sides of the headland, leading to caves forming on both sides. And where there's two red blobs that I've just drawn on using Microsoft Paint, you can imagine that caves are forming on both sides of this headland, whereas the beaches to either side, it says quiet beach there. What it means is that wave energy is going to be dissipated there, and the beaches will actually be constructive waves, whereas on either side of the headland you'll have destructive waves, and that will lead to caves forming on both sides. What that will lead to is the concept that the two caves can join together to form an arch, as you can see in that image at the bottom. The sea will have even more suspended sediment now than it had previously because of the erosion of caves on both sides of the headland, meaning that more and more breccious sandstone is within the sea. This therefore means you have more and more abrasion happening, which will continue to widen and deepen the caves. One cave will eventually join with another on the opposite side of the headland due to that process of wave refraction, and this will, when this occurs and a join is made, you form an arch, which you can see in that diagram at the bottom. An arch is that idea where it's broken through the headland and you can essentially walk through the headland underneath it. That is the formation of an arch. Now then, the arch itself, this is probably the most complicated bit of this explanation. The arch itself will now be worn away in two fashions. You'll continue to have the sea undercutting and widening both sides of the arch, making it less stable. And what I mean by that is if you stand with your legs together and then slowly widen your legs apart, you'll become less and less stable until a point where your body will either fall forward or backwards, unless you can do the splits, which if you can, then congratulations. But the idea is the arch won't be able to do the splits. It will undercut until what the bottom of the arch, if you will, is holding the roof of the arch. It simply won't be able to hold that anymore, and it will drop it. So the idea there is because the bottom of the arch, or the arch legs if you want, is being undercut, what's being held up above the arch roof, it simply won't be able to support anymore and it will fall down. Remember that slam dunk sentence, the force acting on the arch roof will be greater than the resistance to movement. The second way links us back to the European shag and the grass and trees that we mentioned on the first slide. Those will also weaken the composition of the arch roof. You have freeze-thaw weathering at Langston Rock in the winter. That will break the sandstone, or breccious sandstone I should say, apart on the arch roof. And in addition, the shagbird nesting there will also wear away the rock underfoot, weakening the rock. If we add trees and grass here, the trees and grass roots will go searching for water throughout the rock, widening and cracking the rock, making it less stable, making it less cohesive, or less well stuck together, if you will, and that will then lead to rock falls as well. Yeah, your two processes will eventually wear the arch away, leading to a rockfall event. The arch roof essentially will collapse into the sea. Well, actually, it will collapse in between the gap, really. There's your slam dunk sentence, black and underlined. The rock will fall because the force acting on the rock is greater than the resistance to movement. What this will leave is an unattached rock, or a pillar, if you will,
which is called a stack. Now if you look at the image in the bottom left, this hasn't happened at Dawlish Warren yet, but hopefully you can see that this process is going to happen. If you look at the arch roof now, can you see there's quite a large crack running straight through it, which is where that rock is being weakened by weathering and eventually will fall. The kids there in the diagram should probably have hard hats on, if I'm being honest, standing that close to it, but eventually that's going to fall and eventually you will get a stack. If you're not sure about stack, have a little look on the image at the top here. There's your stack. It's an isolated pillar of rock which is not attached to the headland.